Okay, so for our next equation, we have the horizontal wooden beam in the lobby of a new hotel is going to be supported and loaded as shown below. Draw the shear and moment diagrams for the beam. So first step, draw a free body diagram. It's always our good starting point. Okay, so for this here, we have, we're going to call this point, we're going to call this A, and then we're going to call this point over here B. So A and B. Okay, so from here, we have our an upward force at A. We have this reaction force, force A, and then we have this distributed load. So we're going to do the equivalent point load, which we know is the center. It's right at the center. So we're going to just draw it here. And it's 100 pounds per feet. So 100 pounds per foot over 3 feet equal to 300 pounds. So our point here, 300 pounds. Okay, and then another 3 feet over, we have this downward force of 600 pounds. And then we run into another distributed load. Same thing, it's 100 pounds per foot spanning over 3 feet. It's going to be a downward force of 300 pounds. And then we have this force. We have this force at B, the upward force at B. So a reaction force. And we have this final distributed load. It's 50 pounds per foot over 4 feet equals 200 pounds. And then our midpoint of that is going to be 2 feet over. So 200 pounds. Okay. And then the distances separating all of these, this from here to here is 1.5 feet from there. And then from the equivalent point load to the 600 pounds, that's 4.5 feet. And then from the 600 pounds to the second equivalent point load, another 4.5 feet. And then from our, let's do this, from our equivalent point load to our force B, 1.5 feet. And then force B to our last equivalent point load is 2 feet. Okay. So this is our start to free body diagram. And then the total, so if we do this, this is 12 feet from here to here. And then we have this extra 4 feet out here. 4 feet. Okay, so this is a good start for our starting point. Okay, now we do our moment equations. Let's do those. Okay. Sum of forces in the y direction. So start with the positive force A, right here at the far left. Then minus 300 pounds. Subtract another 600 pounds. Subtract 300 pounds. Then adding, we're going to add force B. So this force B right here, we're adding that. And then subtracting 200 pounds. We subtract when they're the downward direction, not downward's negative. That's equals 0. And then moment at A. We're going to do our moment at A to get rid of our unknown. So we're going to have force B from A to B is 12 feet. So 12 feet times force B. And that's going to be positive because it is in the counterclockwise direction. Counterclockwise, when we're talking about moments, positive. This is our positive direction. And then we have this 300 pounds, 1.5 feet away. That's going to be negative. It's pushing down. It's going to want to curve this way. It's going to want to go clockwise. So 300 times 1.5. Then we have 600. We're going to have our 600 pounds. 600 times, and the 600 is a total of 6 feet away from point A. We can see that using this, it makes it really, really clear. It's going to be 3 plus 3, 6. So 600 minus 6, or minus, it's going to be the negative because it's going clockwise, times 6. 6 is how far it's away from force A. And then from there, we're doing minus the other equivalent point load, minus 300, and that is a total 3. That's going to be 10.5 feet away from our force of A. 10.5. And so then we just have our remaining 200 pounds, which is our last equivalent point load, minus 200, and that's going to be 14 feet from force A, from our point A. So we can take this, use Wolfram. You can do it yourself, however you like to do it. But it's going to give us this equation is going to give us that force B, our moment equation that is, force B is equal to 833.33 pounds. And then we can take that force and plug it back into our equilibrium equation for the forces in the y direction to get FA is equal to 566.67 pounds. Okay, so now that we found our other forces, we are going to redraw our free body diagram and then find our shear and moment diagrams. Okay, so first we're going to start with this force over here. We found this. We found that to be 566.67 pounds. And we still have this distributed load. We have this. And that's 100 pounds per foot. And then we have from there our 600 pounds, this downward force, 600 pounds. And there we have our next section is where we have 2 more distributed loads and the upward force here. So we'll draw those. And this one was 100 pounds per foot, and this one was 50 pounds per foot. And then we had another upward force here, and that was 833.33 pounds. Okay. So now that we have our free body diagram redrawn, we're going to go on to our shear moment diagrams. So we're going to start off with our shear diagram. So we see we have this upward force of 566.67 pounds. That means we're going to start off on our diagram, we're going to start off up here. And this is going to be 566.67 pounds right here. That's our starting point. And then from there we have this distributed load of 100 pounds per foot. And that is spanning over 3 feet. So since it is spanning over 3 feet, we're going to multiply 100 pounds per foot times 3 feet, which is equal to 300 pounds. And with that, we're going to subtract that from 566.67 because it's a downward force. So that downward force is going to give us a negative slope that is linear. So it's going to give us a slope that's going to bring us to, if we subtract 300 from 566.67, is 266.67 pounds. And that's going to be connected with a straight line like that. And then we don't have any more forces. We don't have any more force, nothing going on until right here. Right here is our 600 pounds downward force. And what we're going to do about that, we're going to subtract 600 from 266.67. So that's going to bring us down on the graph, and that's going to bring us down to negative 333.33 pounds because we're subtracting the 600 from 266.67. And then from there, we don't have anything going on until we get this point here. At that point, we have this distributed load, and that's also spanning over 3 feet, so it's the same thing that we did before. 100 times 3 feet is 300 pounds, and it's downward, so it's negative, so we're going to subtract 300 from 333.33. That's going to give us negative 633.33 pounds, and that's going to be connected with a line. That's linear. It's linear. And then from there, we don't have any more forces acting until right here, our 833.33 pounds. And we're going to add that to negative 633.33. It's upward, so we're going to add. It's a positive value, so we're adding. And then that's going to bring us up here. That's going to put us at 200 pounds. And then from there, we finish off with our 50 pounds per foot, and that's over a span of 4 feet. So 50 times 4 is 200, downward force, negative 200, 200 minus 200 is 0. So, right there. That's a good check. We're back at 0. It means we did it right. So from here, we're going to move on to our moment diagram. So our moment, we don't have any new moments, starting at 0. So one way we can do this, I'll show you both ways. We could either integrate or we can take the sum. So for this first value here, let's take the trapezoidal sum of this area under the curve, which is positive. So when we have this positive area, we know that we're going to have an upward slope, and since it's a line, and our moment diagram is directly related to our shear diagram, right? You take the integral of the shear diagram to get the moment. It's going to be a curve, an upward curve. Since it's linear, it's just going to be an exponential curve. So we'll take the area under the curve for this one. So to do that, area under the curve. So we're going to start off, this is a trapezoidal sum. So what the trapezoidal sum is 1/2 base 1 plus base 2 times height. So for this first section, 1/2, we're going to say our base 1 is 566.67 pounds plus base 2, which is this right here. It's going to be the 266.67 pounds. 266.67. And then our height is 3 feet, because our height is this right here. And since it's spanning over 3 feet, it is that 3 value. Okay, so for this area under the curve, when we solve this, that gives us 1,250 foot-pounds. And then that means that that's going to be our first point on our graph. So it says right here, and we're connecting this with a curving line, just like that. Okay, and then so we'll do our next section right here. For that, we'll take the integral. So what we're going to want to do is start off with what's our equation for this line right here. So we know that our equation for this VR is equal to 266.67. That's all it is. It's a straight line at 266.67. There's no slope. That's just what it is. So for a moment, we're just going to take the integral of that, which ends up being 266.67x plus c, right? Plus c. We want to know what our constant is here. This is the one, their 1250 value here. That's going to be important for our c value. So for our moment, our c value is essentially the first value we're starting at this point. So our c value for this section is 1,250, and that's because if you're thinking about the equation, think about like how we're like doing this. So for this section, this starting point right here, we're going to say that this is x equals 0 for right here for this section. So at m of x is equal to 0, that's 266.67 times 0 plus c. This is equal to 1250. So that's how we get our c value. That's how we get our c value. So that means that our moment of x for this section right here is equal to 266.67x plus 1,250. Okay, and so from there we want to find out what our next point is, where we're gonna intersect this line. And for that, that's our x equals 3 value, because this is a span of 3 feet. Right here, 3 feet. So this point over here is going to be where x is equal to 3, x equals 0 here, x equals 3 here. So we're going to plug in m of 3 is equal to 266.67 times 3 plus 1250, and that ends up being 2,050 foot-pounds. Okay, and that's our next point on this graph. So right here, and we want to remember that this is going to be a line. It's going to be a positive. This area under the curve is positive. It's going to be a positive line, and just like that, at 250 foot-pounds. Okay, and so from there you can continue to solve this and do this. You could do either of the two ways. You could do area under the curve or the integral. We'll just I'll give you the points for those of what they'll end up being, so that way if say we're going to do the integral for this section, it's going to be the same thing, same idea as what we just did before, and that's going to end up with us having value down here, and that's going to be a line, because a line, again, this is just a straight line, so we're going to have a linear slope, and that's going to 10, 50, and then of course our next point is going to be down here, and that you could take the trapezoidal sum again, or you could do if you're going to do the integral of this section here, so this section, it's going to, the VR equation for that is going to be, that is going to be, so it's actually taking the distributed load, so it's going to be negative 100x minus 333.33. And then for the moment of that, you just take the integral. And you would solve from there. You'd use the same thing, do the same thing with your C values and whatnot to end up getting the right values. And then from there, this is going to be a downward curve. And then same thing here, also slope like this. So that's going to end up being 0. And this is negative 400 foot-pounds. So once you're either doing, you do the area under the curve or the integral, and from there that's exactly how you want to take it and solve it out. Alright, and that's our shear moment diagrams for the beam in the hotel.